Alright, so last we talked, we were discussing MVC, but before that, we were in the middle of talking about testing. And I made a joke last time about operating on a stack, so I apologize for going off on a completely new topic and then coming back to the old topic. But it was necessary, I think, for those of you who want to get started with Sprint 2 and those requirements early, to see MVC so that you can start thinking about the design of Sprint 2, knowing that as soon as possible. I guess I can also mention that the rubric for Sprint 2 only had one change. 5 points came out of design and 5 points are now being used for testing and looking at actual written unit tests. There is a great outcome now in the rubric for writing unit tests for your code. All right, testing. We talked about some of this last time, but I think that this is the most important section of this slide deck. So I'm going to go over it from the beginning, from the top here, because it's very useful. So the different kinds of tests, how they relate to each other, how they relate to the entire software engineering field and development process. Unit testing was that smallest unit of testing. We talked about this concept of white box versus black box testing. White box testing means we have access to the code. We're actually going to be looking at the code line by line and writing tests to see, does this code produce an outcome that I would expect? So microscale testing, we're going to be testing objects, we're going to be testing methods, something that's directly in the code, smallest at scale, performed by the person who writes the code. And they're tested in isolation, meaning that we're not going to be testing any connectivity to other things. We're just testing one small component by itself. No communication, all in isolation. And the idea behind the design of the test is to make sure that this small component is working the same way that the design specifies. So these are kinds of things that you might consider in unit tests. Note that you're not actually testing the communication with the other unit, it's just the interface. We'll actually talk about stubs and mocks later today, because that is usually what you do to be able to test that interface. So write something like a stub for the other component. So we'll get to what that exactly looks like in the unit test, but testing local data structures, testing path through code, so making sure that if you have an if, a test for an if, you also write a test for the else. Some error handling paths, some boundary conditions. Pretty straightforward. You've hopefully been doing this for a little bit, at least in design patterns and in data structures. Integration testing is, again, once people have their individual components together, we're going to start testing the communication between those, determining if they function together correctly. So they're actually putting those components together, focusing on the interfaces between those components. Do those interfaces work? So again, these are done by the developers and designers. You can also hear interface testing or assembly testing. Those kind of help you to understand what it is that these components actually, this testing actually is for. Interfaces between modules, the assembly of modules into the final product. So we're constructing a larger problem from the smaller units. While the smaller units might work in isolation, what happens is together. You note that when it says stubbing lower level units, we're actually going to talk about that, exactly what that means momentarily. We'll actually go into a bit more definite. This is kind of a definition of stub testing. I'll give you some examples of this in a follow-up slide deck here momentarily. But the idea is this: if you're writing a module and someone else is writing a connected module and that module is not ready yet, you can write kind of a default case for that. Instead of actually going through any kind of computation, you write a response. So the generic example that I like to give is maybe an is even method. A stub for that, even though it's a single line, would be something like return true. And that way, whenever you write a test for it, you would see if I pass something that is even and returns true, I can now write a test to see, is that what I would expect? If it returns false, which it will never do, then there's no reason to write a test for it. You can write a stub for any of the particular responses. If I get this response, how does my application handle that response? So you at least need to simulate that response. And a stub will give you the response without implementing any of the logic. So it's just a shell of an object with the purpose of just feeding you back exactly what you're expecting or testing the current model. Does that make sense? So that's big picture of the concept of the stub. So regression testing. We talked about this in brief. So you make some changes, you release a new version of something, and maybe it breaks some of the old functionality, so old tests that used to pass. So we're testing a larger program now that has been changed or modified since these tests were written for it, to make sure that it still functions in the same way. We added some new functionality. Does the old functionality still work the way we expect it to? So you're going to re-execute some of the tests that you wrote in the past. You're going to test the larger system before the modification, after the modification, ensure that no changes happened when you inserted the modification. This is mostly a thing of the past if you use CSCD, continuous integration, continuous development. That's an entire unit that we're going to cover in a few weeks, as well as you're going to get some experience in a later sprint implementing this in GitHub. But for now, it's just important to note that this is what regression testing is. If you write a continuous integration, if you make that in GitHub, then for the most part, you don't need to do too much regression testing. System testing is for the entire system as complete. So it's more black box style. We no longer have access really to the code. We don't care too much about the code. It's does the entire system function. Given inputs, does the system do what it is expected to do? That doesn't require us to understand how the components work. We're going to be able to go look at the code, but to see does it all work together to produce the outputs that we expect it to. So the important prerequisite is the entire system is complete. It's all assembled. All of the modules are done. All of the integration is done. Now we just want to ask from the client's and the user's perspective, as I'm using this application, is it behaving in the way that adheres to the specification? If so, then we'll pass those system tests. These system tests are usually written not from the usability perspective, but can be directly written from the functional and business requirements. So another reason that you write these user stories is that you can eventually write system tests directly off of those user stories. And that's the thing that I forgot to mention at the top of the class. It's a good thing I said that. So once again, user stories are a part of this second sprint. And we can set a deadline maybe a couple of days from now. Say, let's try to get these user stories in so that we can start working on everything else. I did want to give a little bit of feedback on the revised user stories. Hunter is looking through those right now and says there was some improvement, but there are still some significant flaws. So as you're writing this user stories, feel free to, especially in the lab period on tomorrow, it's going to be a strict work day. So don't expect there to be any content in the lab period tomorrow. It's time for everyone to get together and just make progress on sprint 2. Go through a design process similar to before. But this would be a good time to ask me questions about user stories and how good were those user stories, because I want to publish those grades as soon as possible. But I also want to make sure that I've done a pass over those pictures that they're there. So, aside done, sorry about that. So system testing, again, we want to make sure that the specifications are met, the specification document, there's actual implementation for all of that. And we're tying the user stories and scenarios directly into tests for functionality. So you can write these system tests directly off of that communication from the client. Kinds of system tests, you might care about things like recovery tests. When something goes wrong, we want to make sure that recovery is happening. So this is where, again, stubs and blocks are very important. You're going to take the actual working system and you're going to replace it with something that intentionally fails. And that way you can really test what happens when something goes wrong. You don't want to come up with an error case that does that. You can just swap in a functional component for a mock component that creates the error for you. And then you can use that as a system test to say, great, the recovery works as intended. Because the actual full program shouldn't ever need to do that. But in case something happens that you didn't write a test for, it would be great if your recovery does work. Another type of system test is a security test, making sure that, again, you could have an object, you could take the security of your program, kind of turn it off. What happens when something happens that breaches a vulnerability? How does your system handle it? Do the appropriate notifications get sent? Do you get notified that a breach has occurred? Then you will turn your security back on because to the best of your ability, it blocks everything. But in case something does get through, you want to make sure that your scripts that send that notification are running and work. So those would be important system tests. Stress testing and load testing, we talked about this, making sure that your servers are performing up to standard for however many anticipated users you have. This would be maybe a script that makes a bunch of accounts, tries to DDoS the system. So what happens when that actually happens? You have a test that creates that scenario so you can see how your system handles. Performance testing, trying to figure out how efficient is this running. Given a particular query, how long does it take to give you a response? This could also be testing under certain hardware configurations. Maybe you want to try this out on different machines than you originally tried it with, just to make sure that different combinations of hardware don't interact unpredictably with your software. There's migration testing. If we move from one infrastructure to another infrastructure, what needs to change? This happens all the time. Anyone go into some government agency and realize they're still using computers from the 80s? What do you think anything that interfaces with that was written in? Do you think it's any modern programming language? So in design patterns, when we were talking about something like an adapter, or the adapter design pattern, finding a way to write an adapter that says this is expecting some kind of legacy communication, and I now want to map it to something newer than that. You could just write the adapter that converts them if that is possible. Yeah.
More hardware oriented, but where I work, they have an entire like branch of the like people who are supposed to like find, you know, other country stuff and reverse engineer it.
Yeah.
They have an entire like section of that branch, a large section of that branch is just built for not testing on our own stuff, but being like, okay, we have this part that what hasn't been made since the 50s. We have like this many of them left. You need to figure out how to remake this part without breaking any of the ones we already have.
Right.
So like, and obviously software for stuff like that too, but yeah, that is a huge thing, just trying to reverse engineer parts that aren't made so we can try to make it again.
Yes, absolutely. So that's a great example of kind of a system test to try to understand how something works. Yeah, I like to use the adapter analogy there because you're gonna need to connect a round shaped plug to a square shaped hole eventually. So making the round shaped to square shaped adapter in code form so that you can plug that in and make it work is useful, but making sure that when you write that adapter, that none of the, you're thinking about all of the associated changes that might be needed in your code. So their usability testing, we talked about from the end user's perspective. Acceptance testing is when you actually give this to the end users. So actual users are going to test the completed system and come up with, is this okay? Are there any features that people wish that they had? Does it satisfy the acceptance criteria? So this needs to be documented early on in the process. What is going to be the tests that are done to ensure that we have built the system to your specifications? That should be known before you start. When you finish the product, then you should be able to run those acceptance tests on those people to say, can you do this? Yes, all right, that was part of our acceptance criteria. Can you go and do this? Is it feasible? Is it understandable how to do this other part of the acceptance criteria? Great, do it, excellent. If they can't do it, then maybe some change needs to be made to make sure that they're able to interface with how they need to use the system. So this is of course done by the real end users of the system, whoever is purchasing this software from you or the company you work for. The customer gets to say whether this is what they paid for or not, but you should have some kind of legal documentation that specifies what that is before you start, because otherwise you're always at the mercy of your end user, and they will say, of course, this isn't what I asked for, I asked for something else. And if you don't have that legal protection, then you'll end up in court. No one wants to end up in court. Very similar in games to the concept of beta testing. The game is basically done, but maybe there are some very small balance changes that need to be made. You're going to get actual data from end users and have analyze a large number of message board posts, bug reports to figure out what small changes do we need to make before releasing this product. Is it what we promised when you backed us on Kickstarter? So it should be performed in as close to a real environment as possible. If you need to have a simulated environment, that can be fine, but you should design that environment to be as real as possible. You should praise and perform these tests as if the end user is actually doing something. This is no time to have them do toy examples. This should be them actually using the product for its intended end use. So this is banking software. I would like to come back to that in this class. You actually want people to make real accounts, to make real deposits, to go through the entirety of how this system needs to be used with real money. Fully using this system, what happens? Does it work according to what you promised to them? Once this process is done, the customer will sign off on this and completes your legal obligation for producing this product. So acceptance testing is very important for that final handoff. Of course, this isn't if this is the first time the customer is seeing the end results, then we use the waterfall model. We talked all about just how poor that is. They should be involved throughout earlier testing phases, throughout earlier iterations of the production of this product. And of course, we talked about how acceptance criteria should be established as part of the requirement specification. Acceptance testing, in all bold, I've already said it, verifies that the system satisfies those requirements. Of course, there should be some implied requirements for things like quality and performance and usability, even if they don't specify it outright. If it takes 20 seconds to load something from your server, it's not usable. It doesn't have the level of performance that they shouldn't have to specify that as part of it's usable. You should come up with something that is efficient enough to be able to handle their requests in a reasonable amount of time. That should also be part of any legal documentation that you have, but in case it's not, assume that the client's here matters and that you're designing something that's intended to be usable. Alpha versus beta testing, useful in games, used in games, but it's also used in the production of many large-scale software systems. So alpha testing usually involves simulated data versus beta testing uses real data. So this is why the users more so get involved in the beta phase rather than the alpha phase. The alpha phase is when you're going to make a bunch of fake users who interact with the system in simulated ways. So real people are expensive. Unless they're playing a game, in which case users are pretty cheap. Everyone wants to play a game, but if you're actually trying to do real stress testing on some software that you've written, you're probably gonna have to pay real people to do it. Which is why writing a developer or paying a developer to write scripts to interact with the system could be significantly cheaper than hiring people to use the system and give you feedback. Especially if it's something that can be simulated, which is why we go through an alpha test before we go through a beta test. Hold off on using real people as long as possible because people are expensive. All right, we're gonna dive into a little bit more detail about black box testing and white box testing, and that's kind of where we'll end here. So black box testing, again, just focuses on the functional requirements, and it doesn't require you to have access to the code. We're looking at the program's behavior given particular input. Not looking to make it crash in a particular way, that is, if I feed it this input, does it do what I expect? Rather than, does this internal logic work that I expect it to? So when we say black box versus white box testing, it is very important to note that it's not one or the other, you will need to do both. But thinking about what kinds of white box tests and what kind of black box tests we need to do, that becomes important at many different levels in the testing hierarchy. You can imagine how black box testing is used at the integration and systems and acceptance test levels, because at the integration test level, one module is going to be communicating with some other module, so you don't know how it works. It's just a matter of, does it return to you what you expect, yes or no? And that's a way to test that other module, is by saying, do I interact with it the way that I expect? That's the integration black box test. You're not looking at or understanding any of the internal logic of that other module. How do you write a black box test suite? If you're thinking about any of the following questions, it's good to write a black box test suite. So how can the functionality be verified? Because it's the actual end functionality and not the internal logic. How can system performance be tested? Again, that has nothing to do with that internal code or logic. How can system usability be tested? Which potential classes of input make for good test cases? What happens at the boundary of normal input classes? This is, again, if you have a Boolean that changes from true to false at the value 5, test 4, 5, and 6 right by that boundary to make sure that the less than or equal to 5 works. The not less than or equal to 5 works, and the exactly equal to 5 works. So testing right at the boundary. What happens when you give it something that is right on the edge of a branch? What combinations of data or actions should be considered or considered normal? What is an edge case? What is an error case? What is expected and not expected? What does the system do when it's given something that it doesn't expect? All of these are questions that you can ask by just playing with the system, not looking at the internal code. You could use an executable rather than the actual source code to test all of these things, which is why testers exist. You can hire external testers to test your program without sending them the code. But you can only do this for black box type tests. So what kind of documentation should you be doing as you come up with your tests? So first of all, you need to plan for your tests just as much as you plan for your code. You want to make sure that you also test the documentation. That doesn't necessarily mean write code that's gonna use the documentation, but it should be part of the acceptance criteria. To say, can some end user who's never used the system install, work with, and troubleshoot anything that comes up during normal system use? One thing that you might do as part of this acceptance test is redact one of your help menus or help things, and you would then do a study with two different kinds of end users, one who has access to it, one who doesn't, and see how frequently do they have issues with something. That would test your documentation to say, is this useful? Does it actually solve the problems when they arise? All of your help functions should be tested. Any helper function that exists that's not directly able to be called by an end user, you should have tests for all of those. Any documentation errors certainly lead to frustration in end users. So knowing that your documentation isn't good enough is something that is useful in how you learn how to develop how to write documentation. So some examples of things like capacity planning. Trying to figure out how many people are going to be using this. So just plenty of examples of this. So to read one of them. One company's growth meant that it was planned that 217,000 members were going to use it, but eventually the membership exceeded 1.5 million and it wasn't designed for that level of growth. So planning for not just using it today, but how popular is it going to become? Looking at the company, what is the company's anticipated growth over the next some number of years? Build that into the capacity planning for your own application. Kinds of questions that don't often get asked. You develop something for today, and a few years from now, suddenly your entire design isn't good enough to handle the load. So do note that things like infrastructure planning can be very expensive mistakes. That can cause all sorts of issues, from hardware failing that needs to be replaced, to new software that needs to be created for it, network hardware, network equipment. If you don't plan, money flies out of pockets. The other big part of testing that kind of can use some examples is security testing. I again like to go back to the bank example because it's pretty universally known. But as an example, you can hire a company that can attempt to break into your system. And this becomes a great way to test this. Actually pay someone to attempt to hack into your system and reveal and document all of the vulnerabilities of your system. Maybe that's cheaper than thinking through and writing a bunch of tests and hoping that you've got every possible security vulnerability. Leave it to the security experts. Leave it to the cyber majors. They know what they're doing.
Eastern, excuse me, reference, Eastern just paid $200,000 for 3.5 weeks, 4 weeks of that.
Yeah,
So
it's a lot of money,
Yeah.
but what is the cost of
those people.
a lawsuit that involves that many end users? Just look at all of the examples of large companies that had to pay out significant amounts of money to these kinds of vulnerabilities.
So for reference, there's a couple cyber majors in this class, so do we really know what we're doing?
The answer is by the time you graduate, it should be yes.
Should.
But there's a purpose to all of us, right? And there's a specialization out there for all of us. And this is one of the places that you want to go to a security expert rather than hoping that your developers are security experts and find every possible vulnerability of your program. It's never gonna happen. All right, we're gonna do a deeper dive into integration testing, because this is the next level of testing from what you have seen in unit testing, and I like this because it introduces the concepts of stubs and mocks that are actually used at the integration testing level. So I'm expecting that people are coming into this with a reasonable knowledge of how to write a unit test. You've seen a unit test, so now we're gonna be looking at how do we move forward from unit tests to test larger subsystems. What needs to change when you integrate 2 or more units together? So I'm gonna skip a lot of this intro, we've talked about most of it. If you have some kind of big bang integration, that is everyone is doing everything separately and then you combine them all without a ton of testing, you just kind of hope that everything works. And you can see how different components of common programmatic structures like global variables, that can be a big vulnerability when you're trying to access some aspect of some system that you didn't write. If you're modifying a global variable, every other system that thinks that global variable isn't being modified is now suddenly very curious why one of its variables has changed values. Error handling assumptions, any encapsulation that's not strong encapsulation, an interface that hasn't been documented well, stuff happens and the end result is a mess. The idea is we're going to integrate in pieces. So we have the entire system. You can imagine this is kind of how we concatenate to an empty string. You instantiate a variable that is the empty string. It contains no information. And as components are done, maybe as a toString, you're going to add that to the existing empty string, concatenate, giving more and more and more information. So this incremental integration is going to start out with the complete project, which is the empty project. All the completed components, there are 0 completed components. And we're going to integrate as those components start to get finalized and completed without the communication associated with them. So you can see that when we integrate this component, we can't test it with any of these existing modules, but as things get added to it, we can start integrating and making sure that these integration tests are working and functioning, and these components are actually integrating together in the final project. We integrate the piece with the skeleton, whatever the state of the skeleton happens to be. Interface with the modules that are already complete. Make sure you write those tests. So benefits of incremental integration. An error is easier to find and easier to fix. Great. You always have a system that mostly works, even if there's missing some functionality. The actual system mostly works, at least according to the best knowledge of the integration test we've written. This means that you can always send a working version of something to the customer that says, here's what we have so far. We don't have this functionality or this functionality, but it doesn't break the entire system that I don't have this functionality. The drawbacks, of course, is that to really test those components before the components that they rely on are complete, we need to write stubs. We need to create either fake objects that are going to be mocks or fake behavior that we're going to call it stuff. So how do we actually think about integrating? There are 3 main ways that you can think about this integration. So this would be something like a UML of a completed project. So here we have some dependencies between these classes. We can see that some of these are inheritance, some of these are just directed association. But if we wanted to write integration tests, we would start with the outermost layers, kind of the user interface layers, and start to work inwards. What does this mean? How could you reasonably test a user interface where none of the buttons did anything? None of the functionality is there. The actual user interface is there, but nothing does anything. That's kind of a top-down approach. Start with the UI. But you can start with kind of the customer. Does this UI layout look nice? Does this menu layout make sense? If I asked you, how do you print the this current design, if we're doing a UML editor, how would you go and print it? It doesn't matter that the print functionality hasn't been written. Can the user go identify where to go print the UML diagram? So that kind of functionality can be tested very early in this process with top-down integration, because the UI is done, we haven't built the functionality into the UI yet. So that's one way you could do that. And now we could say, all right, now that we've done these subcomponents of that, none of this underlying functionality works. We can at least click on something and see a pop-up. Maybe that pop-up doesn't really contain much aside from some text, and it doesn't allow them to do that. But now you can start to test the system at a shallower level and a shallower level as you start implementing those. So that's known as top-down integration. You could also start from the other end. You have bottom-up integration. Now we're gonna be writing the logic first, the low-level data structures, the low-level logic, making sure that's working. Once it's working, we combine them together into a sub-module that where all of this associated logic all works together. Great, but note that we still don't have the UI done to be able to test the usability of all of this. We just have all of the logic done. We have to simulate running it through a user interface. This means we don't figure out the high-level issues until very late in the project. And of course, the way most of us do it.
Yeah.
The sandwich integration. And this can actually make sense. So you kind of start from the top and the bottom simultaneously and work towards the middle. If you start at the top, you're going to be having a sub-part of your team working on the user interface. Another part of your team working on the low-level components. The issue comes when you try to integrate them in the middle. You have to have a really good design for this, because what the user interface is expecting has to be exactly what's being produced at the lower end. So this works really well only if your design is really solid. If your design is not solid, then you're gonna have a ton of merge conflicts, a ton of issues with this feature is supposed to be implemented. Oh, was it? I never implemented that. Oh no, the due date is in 30 minutes. Those kinds of issues show up when you do a sandwich integration and there's no communication between the UI and the logic. But that said, if that communication is there, this kind of has the strengths of both. So this is really the ideal way to do it. It's really practical to be able to do this, but only if the design is good, if that makes sense. So we've talked a bit about daily builds. I'm not going to go through this. We talked a little bit about some of the challenges of integration testing, but I want to pause here just a little bit to talk about when you combine these, they can fail in more places, in more complicated ways. It's worth knowing just how many places an integration could fail. So the big question that we're going to be talking about, I don't think we quite have enough time for this. We're going to start with it, I guess, on Thursday, is how do we test a partial system? How do you actually test a system where not all the components are there or implemented yet? And this is something that we run into a lot in this class when we give lots of different developers different components of a project that all rely on each other. So how do you continue to test your piece before the other piece is complete? You can't just sit there, twiddle your thumbs, wait for the other piece to be complete and then test it. You want to start having something to do, being able to write some of these stubs and mocks into your code so that you can test that functionality in better detail, so that you know what problems are there and you can find them faster. Is it more work overall? Yes, but it will take less time overall than waiting for your partner to finish that component. In this class, you may want to trade off writing stubs and mocks versus communicating with that person and going and helping them out. Maybe your time is better spent in helping them finish their component and then integrating it and testing it. You shouldn't need to write too many stubs and mocks in this class. That said, in industry, that's a lot of what we do. A lot of writing stubs and mocks. So we're going to define those and talk about exactly what they are, get some examples with them at the start of class on Thursday. I will see you all tomorrow for lab time. Hopefully getting some design underway. Really work on print too. 4 teams I have not yet talked to about sprint ones. Feel free to stop by my office and look at our chat. We're in public channel, so I'm gonna need that study guide to you. As soon as I-
Stop making this fun.